Morning. So the first thing we're going to cover is electron configuration. So the electron configuration usually has the form of one. So one is the level. So there can be 1, 2, 3, 4, 5, 6, and 7, I believe. There's S, which is the sublevel. So sublevels you have S, P, D, F. And those are your sublevels. Then you have the number of electrons that are filled to get to your element. Okay. So once you have, this is the standard configuration. So this is only for the S orbital that we're covering first for the example. So electron configuration has this. I would recommend for you guys to take a picture of this table. It tells you which columns, which rows fall into what for electron configuration. So the elements covered for this will be the 2s. Elements in this row right here will follow the 2p. The only difference will be the change in the number for the electrons, which would be this number right here. So take a picture of this, and we'll go on to the next one. We can come back later. So how to write electron configurations. So the first thing is that the number of the row indicates your principal energy level. What I mean by that is, this is why we have these numbered as 1, 2, 3, 4, 5, 6, 7. And that's because those are the different energy levels as well as how much further it gets from the nucleus. So the next thing to know is your column. It indicates the type of sublevels. So earlier I said that we have an S, P, D, and F sublevel. You guys can refer to it again right here. This is your S. This is your D. This is your P. And this is your F. So the full electron configuration indicates everything from one s orbital all the way out to the valence electron orbital. So the number of electrons can be found using the atomic number. So for noble gas electron configuration, what you'll be doing is you're going to use a noble gas to basically be a stand-in for, so let's say if you have 1s, 2, 3, 2, 2s, 2, 2p, 6, 3s1, okay? So if we do the 3s1, you can put the noble gas here and then just have 3s1. So it basically takes up the space for all the way from 1s2 to 2p6.
I have a question.
Yeah. Mm-hmm.
So when I just write it for the box like 3s2, do I still need to write 3x1?
Oh, sorry, I meant 3s1. Yeah, I meant 3s1.
So just put the box to write 3x1, right?
Yeah, so in this case, so if we look at the periodic table, okay, we'll go to this one right here. So we'll look at the periodic table. This is your 2p6. You'll look at the noble gas here, and in this case, it's neon, right?
Mm-hmm.
So if you were to rewrite this, you would write neon in here. And that would be your noble gas configuration right here.
Okay.
This is noble gas. This is your full electron. And that's because it contains everything from the first energy level.
Mm-hmm.
Yeah. So let's go into the next slide.
Okay.
So this one, so I want you guys to do this. We can do this one together, and then you guys can do the next one on your own. So we're looking at magnesium. So let me just, I'm going to highlight it. Where's magnesium? Magnesium is right here. We'll do 2s. So this is 2s, 2p, 1s, and then this is 3s. So we'll notice that it's 3s2 right here, because that's 2 electrons. So the full, I'm asking for the full configuration. The full configuration would be 1s2, 1, 2, 2s2, 1, 2 again, 2p6. You completely cover everything in here. And then you have 3s2, because magnesium is the second element in that row. And you can also count the electrons. So there's 12 electrons. So it's 2 times 3 plus 6 equals to 12 electrons. So from here,
asking, sorry,
yeah.
why 2s6?
2s6. Did I write s?
Do you mean 2p6?
2p6. So 2p6 is because there's,
yes.
So you'll take 1, 2, 3, 4, 5, 6. So you're just counting 1 electron per row. I mean, per column. So it's like if you look at this previous one right here, all of these add up to 1, 2, 2p. The p, when you're looking at it, it means the number of electrons in that orbital. And you'll see right here that there's 6 electrons in the p orbital. But if you do s plus p orbital, there's 8 electrons total. So that's typically how much you have in your orbital shell when you're counting your electrons. Does that answer your question? Okay. So now if we do the noble gas, earlier how we did neon, you'll see that you'll go to the noble gas before your element. So the noble gas before magnesium is neon. And then you'll have 3s2, and that's your noble gas configuration. Neon takes the place of 1s2, 2s2, 2p6. Okay, questions? You guys can do the next one. I'll give you guys 3 minutes, 7:20. So 7:20 to do this one. If you guys finish early, let me know. We'll start to the next one. You guys see? Okay, so I wrote how it came out. Let me know if you guys did not get the same. So I noted that we covered the 1s orbital, the 2s, the 3s is completely filled, 2p is also filled, and here for 3p, I numbered it. So 1 electron, 2, 3, and 4. So the first thing I did was I wrote the full electron configuration of sulfur without the sulfur ion. So for sulfur, you'll see that you go completely to 3p4. What that means is for the noble gas configuration of it, it would just be 3s2 and 3p4. Then to do the ion of s2+, notice that sulfur has a 2+ charge. What that means is you have a loss of 2 electrons. So when you lose electrons, you have a positive charge, and you lose your electron from your outermost energy orbital. In this case, it's the p orbital. P orbital is further than the s orbital. So your configuration changes from 1s2 from 3p2, 3p4 to 3p2. And that just falls into the same with the noble gas configuration as well. Any questions? No? Okay. So we'll go on to the next one.
Yes,
Oh yeah.
I have a question. Can you explain one more time for the noble gas, please?
Yeah, so noble gas, you'll take the noble gas in the row before your element to do it. So think of it this way. You can't use argon because if you use it, argon is completely filled, is a 3p6. But your sulfur is a 3p2. Your sulfur ion is a 3p2. So if you use neon, it's just shorthand. It's a shortcut for you to not have to write all of this. All of this, I mean. Your noble gas just fills up everything before 3s. So 1s2, 2s2, 2p6. That's the electron configuration of neon. It's just a way to make it so you don't have to write, like, let's say you have to go all the way to the d orbital, or you're writing the electron configuration of V, you don't have to write everything out. You just write things in the 4s orbital, in the 4 energy level. Do you see what the noble gas is used for now?
Yes, I think so. Yeah. Thank you.
Okay.
Excuse me.
Yeah.
Can you explain the second two mean loss of 2 electron to the other orbital or from outermost orbital? I don't understand this one.
So we'll explain the atomic orbital in the next part, but basically what I mean by that is your s orbital is your innermost orbital. So if you think about the nucleus, you have like an s orbital. Your p orbital is a little bit further. Then you have your d, and your outermost is your f. If you think about it that way, that's just what I mean by outermost orbital. Your p orbital is your outermost.
Yeah, got it.
Yeah.
Someone's asking, do you always use neon to get the noble
gas?
Yeah.
In this case, it was just neon was my example. The next one actually will not be. Double checking if neon will be the noble gas or not for this one. It is not neon for the next one. It was just that it falls into. So you'd use neon for the noble gas configuration for all the elements in this row except for argon. You'd use argon for the noble gas for all the elements in this row up to before krypton. So it's just coincidence that my example before was also for neon, used neon. So let's do the electron configuration for 3. You can just do the full electron configuration for zinc. You don't need to do the noble gas one, but do both for the zinc ion. Okay, we're going to go over it. So I asked you for the full configuration for zinc, and then zinc full and noble gas for zinc ion. So for zinc, you have a full 1s orbital, 2s, 2p, 3s, 3p. Now you go into your 4th energy level. So you have 4s. But here's the funny thing about your periodic table is that this transition metal section right here will actually fall in the 3D. It won't be 4D. So starting from transition metals, you go one back for the D for the D orbital. So it's 3D, and zinc is here. So if we count it, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's completely, the 3D orbital is completely full. So zinc is annotated as this, where 3D is full all the way. 4s goes before 3D when you're writing it as well. So zinc 2+, you have a loss of 2 electrons, and it's lost from your outermost energy level. So did you guys take it from the 3D orbital or the s orbital?
D.
So, but your d orbital falls into the 3rd energy level, not the 4th energy level. So is your 4th or your 3rd out further? Higher. So so the 4 is even further than 3D. So that means that you have to take your electrons from your s orbital. So that's why I subtracted 2 from the s orbital, and I wrote 4s0 for the electron configuration. Does that make sense to you guys?
Yeah.
Yeah? Okay. So given that, when you write the noble gas configuration, I looked at the gas before this row, and it was argon. So argon takes place inside the brackets, and then you put 4s0 and 3d10. Questions? We'll go more into I'll explain more about the orbital differences in the next section.
So 3D is energy, 4 energy, right? 4 level energy.
Yeah, so the fourth energy level is further than the 3rd energy level.
Okay.
So that's why when I say the outermost, it's the one that's furthest. So 4s is further than 3D.
Why 4s0?
Because you take 2 electrons. You lose 2 electrons. That's why you have a 2+ charge for the zinc.
Okay, thank you.
Mm-hmm. So for this one, I would say again, take a screenshot of this. This table would be so helpful. It tells you guys the valence electrons, which means it's your last 2 that you'd write down for the full electron configuration. Let me know when you guys are done taking a picture. It also color codes each of the orbitals for you too. Are you guys good taking a photo? I'm going to move on. Okay. Okay, next section. Atomic orbitals. This is where it answers some of your questions for orbitals. Okay, so this is how you'll typically see it. So you'll see that they denote the P's and S's. So S has only one line, but the P has 3, and D has 5. The F has 7. And that's because this is when we're going to draw arrows in a sense. So usually you have one arrow. So if this is 1s2, you'll have 2 arrows like this, and they're going in opposite directions because of your Pauli exclusion principle. And what that means is that they go in different directions and they don't go in the same direction. Okay. So because of that rule, so they don't have the same spin basically. So that's why they have to go into opposite directions. And you're just going to fill. So if you'll note that you fill them each in the same direction first, Then you go back and fill. If it was filled like this would be a 2p5. So this is just how you would fill energy levels if we're asking you to show them. Okay. Next slide. So in summary, this just tells you how many electrons you can have in each of the levels. So for the S, the max you can put in is 2. That's why you have 1. For P, the max you can put in is 6. And that's why you'll have 3 lines and you'll fill them. Not everything is full. It's only ever really full when you have a noble gas. P is 5. That gives you 10. And then it's 7. 6, 7. And this is just it being filled both. So that's for 7. You can also take a picture of this if you want, but this is just gives you a guideline of basically how many electrons you can fill for each sublevel. Okay, so this is your first example.
Someone's asking, what
Yeah.
does higher and lower level of energy mean?
So a lower energy level would be, let's say we're doing, so there's 7. So if we're comparing level 3 to 4, if you're jumping from 3 to 4, you're going from a lower energy level to a higher one. So that's what I mean by going to a higher energy level. Okay. I don't know why it's not here, but basically what I mean by paramagnetic is that if something is paramagnetic, it has an unpaired electron, unpaired electrons. Tron or trons. Diamagnetic means paired. Everything is paired. Paired electrons. So we'll do this one together. So if we're drawing the atomic orbitals for oxygen, oxygen is here. So you know 1s is filled, 2s is filled, 2p is not filled all the way. So it's 1, 2, 3, and 4. So you can write 1s. When you're doing these, you can do them in a line unless your professor specifies they want it on the scale. Usually they'll just say, list them all out or write it all out. So 2s, and then you have your 2p. 2p is all 3 of these. You can do a little bit more of a distance from them. So 1s is filled, 2s is filled. Now we have to fill each orbital first once before we go back in to fill them again. And what that is that it's Hund's rule. So Hund's rule states that you have to fill them each before going through again. So there's 1, 2, 3, and 4. This is oxygen. So based on this atomic orbital drawing, would you say it is paramagnetic or diamagnetic?
Para.
Yeah. So this is paramagnetic. So just recall this because the next 2 problems I'll also be asking you to tell me if is it para or diamagnetic. So let's do this one. You guys can do this one on your own, and this is copper 2+. So determine whether it is diamagnetic or paramagnetic. I'll give you guys until 46 to do this. Are you guys okay for us to start this?
Uh-huh.
Okay, so let me just show you guys. So the first thing I did was I wrote out the full electron configuration. You can write it as noble gas too if you want, as long as you know how many is in the outermost. So copper is usually is usually 4s2, 2 and 3d9. Since it has a 2+ charge, you get rid of the electrons in the s orbital, so you have 4s0. And that's why I show in this that there's nothing. So I filled all of these. I filled all of these out. And then I showed 3D and it's 9. So is it so did you guys put down paramagnetic or diamagnetic for it?
Para.
Yeah.
Para? Okay, yeah, that's good. Did you guys have any questions on this one?
I have a question. My initial thought was that pulling from the 4S, like I pulled from the 3D first because it was already not full. Do you know what I mean?
Yeah. So here's that's the tricky thing with your with them, because if you pull, you'll pull from the 4S because it's your outermost. There are some elements where you might actually pull from the 3D, but that's usually rare.
Okay.
To balance, because you might want to have that 3D5 is a better number than a 3D8 or 7.
Okay, so just like the rule is the furthest
Yes.
you pull from, whether or not that 3D is full or not. Okay.
Yeah.
Thank you.
So any other questions? We'll go on to the last one for atomic orbitals, and then we're going to go into periodic trends. Okay. So for this one, how about we do this together and you guys can get, so that we can go on to periodic trends, and you guys can do a challenge problem for this one after. You'll get a challenge one for it. So you guys can all chime in, just tell me where. So first is Ca2+. Can anyone do the, tell me what the electron configuration would be? So calcium is here. It has a 2+, and it's from the 4s2. What would it be?
Okay.
The B is 1s2, 2s2, 2p6, 3s2,
Okay.
and 3p6.
Yep. So it's basically, Ca2+, it's basically almost the same as argon. It is the same electron configuration as argon. So when you're drawn, 1s, 2s, 2p6, 3s, and 3p, 2, 3, 3p. So we'll fill these up. So is this paramagnetic or diamagnetic?
Someone's asking, so is it always going to be paramagnetic unless it is a noble gas or an ion that results in the same number of electrons as a noble gas?
No. Well, if you look at it, zinc is diamagnetic, and it's not a noble gas or an ion, because zinc is completely full to the 3d10 and 4s orbital. Yeah, so zinc right here, like these elements in this like section of the d orbital, if paramagnetic is just anything that is unpaired. So zinc doesn't have any unpaired electrons, it's completely full. Your noble gas are also diamagnetic, but so is calcium when it's on its own. So really anything towards the tail end of that s orbital, that p orbital, that d orbital, where it's full. Okay, so here is periodic trends. We'll go over 4 of them.
And I'm sorry, did you, for this example, it's diamagnetic or paramagnetic?
It's diamagnetic.
Okay, just making sure. Thanks.
Yeah. Oh, sorry. I don't know why all my writing didn't show up. Sorry. Yeah, so zinc, calcium, those are other cases where it's diamagnetic as well. So now we're going to go into periodic trends. So this is atomic size. So you guys should have this, write it on your periodic table. You guys take a picture of it after. Rubidium. This is what happens when they go increasing and decreasing to you. So really right here is in this direction, you're increasing in size and decreasing when you go up. So in this case, rubidium is the largest, xenon is your smallest, if you're comparing them in this row. But helium is the smallest versus xenon, which is larger than helium. So it's very much in context as to what element you're referring to. So here we're going to rank them in increasing size. So we have potassium, titanium, krypton, and astatine. So let's look here and we can just put them through. So I'll color them. So we have potassium, titanium, krypton, and astatine. So how would you rank this? Can someone?
K-R-A-T-I-K.
So Kr smaller than As, which is smaller than titanium, which is smaller than potassium. Yep. I probably should have scrambled that more for you guys. So we're going to go on to the next periodic trend. So this one is electronegativity. You're increasing as you go to the right and as you go up. So right and up is increasing electronegativity. Your most electronegative element is fluorine. So this one is rank them in order of increasing electronegativity. So I'll just.
Sorry, I interrupt you, but I have a question for about the from the up to the bottom is decreasing, right? From the up to the bottom. Is the increasing or decreasing?
So it's increasing as you go to for this. Yeah, so it's yeah, so it's increasing this way and increasing this way.
Mm-hmm.
So it's decreasing as if you go down or to the left.
Thank you.
Mm-hmm. So I put it here. How would you rank these if in electronegativity? So fluorine, we have fluorine, we have phosphorus, boron, and oxygen. So which one would be the least electronegative?
Boron?
Yeah. So it would be boron, then,
Phosphorus?
yeah,
Oxygen and fluorine?
then fluorine. Yeah. So a good thing to remember really is that your most electronegative ones are in this area generally, and then they just decrease as you go out. So this is the only problem we have for electronegativity. So we answered that one. Now is ionization energy. Ionization energy is just basically how much energy is required for it to go to the next energy level. So we'll keep this chart, and it increases in ionization energy as you go to the right and as you go up. To the right and when you go up. So it's basically the same as your electronegativity. So I'll give you guys more time to do this one. We'll do 5 minutes. And if you guys don't finish, we'll go over the last however many we have left. So 8 to 8:05. Let me bring this over for you.
Someone's asking if you have a table for the electronegativity values.
I will look for it. I'll send it to, I'll email it to you guys along with the recording of the video.
They're asking if it's through an octet rule.
Yes, I believe. I can confirm, but it's kind of similar. It can be dependent on some cases, because I do know that in some cases we might want, again with electron configuration, we might want a 3D 5 versus a 3D 6 or 7. And that's just because.
Part of the shared, sorry.
Is this part of the shared octet minus available? I'm actually not too sure about that. I can look up more about it and get back to you. So I'll just email you guys to answer following questions. So if you guys have it, type it in and I'll try to answer them and send it out tomorrow. Okay. So are you guys good with this one? Can I share the answer?
Yeah.
Okay. So I had to cut these out when I was explaining that basically. So did you guys get the same answers as me for problem 3? If you didn't, let me know. Did you guys? So really, I based this off, if you look at carbon's number is much higher than aluminum. That's what I did for all of them. And again, this is very similar to the electronegativity ranking that we did. And that's because they have the same increasing basically. So you can rank them in the same way. Did you guys all get the same answers, or yes or no?
Yeah.
Yeah. Okay. Yes. Okay. So I will show you guys now. So now we have our challenge problems. I'm not going to go over them. I'll show it to you guys. I'll ask for you guys, if you guys want to, you guys just get started to meet right away, is take a screenshot of it. And then you guys can, if you guys all know how to schedule a tutoring appointment with a tutor, with myself, Francis, or any other chemistry tutor, so you guys can check your answers for them. So this is your first challenge problem. Let me know when you guys are done taking a picture so I can go to the next one. Again, this will actually also be in the recording. They should either be sent out to you guys later today or by tomorrow morning, the latest. So this is the first problem. The second problem is there a problem you're going to choose the element with the greater radius? Your fourth one, where you're arranging the elements in order of increasing electronegativity. And the last one. So this one is more of an explanation. If some of your professors kind of like those theory questions, this one will be a good one. I would also recommend referencing your professor's notes or the textbook where they talk more about your ionization energies and what they mean. So about jumping to a previous level or a higher energy level. Okay. So that's the end. Thank you for joining us, guys.